So, welcome back, everyone, and welcome to today's mid morning session. We have three talks in this session, each of 40 minutes, 35 minutes for the talk and 5 minutes for the questions. We have a very distinguished line of speakers, the first of whom is Philip Kim, who is a condensed matter experimentalist and a professor of physics and applied physics at Harvard University. And he's going to be telling us about physics in Flatland, searching for new quantum materials for emerging technologies.
Thank you. Thank you, Chairman, and thank you, organizers. Invite me to this nice town and give me an opportunity to speak in this very celebratory the event. I'm very glad to be here and represent the part of the condensed matter physics efforts as a special experimentalist related with the developing of the quantum mechanics and hopefully that using that for some interesting application. I think that's kind of something that I'm going to share today. All right, and also it is kind of well situated right after Huang's talk that we heard that the three-dimensional, four-dimensional space-times to understand that you go to the higher dimensions. My talk is actually going opposite directions. I'm going to reduce the dimension, and we are getting to two dimensions, and that's kind of flatland, right? And there was a very interesting questions, by the way, in the at the end of the talk that we all, including us, including atoms, we all live in the three-dimensional space, right? And maybe four-dimension, including time. What is the meaning of this higher dimension as well as a reduced dimension? Well, I think over the probably half century or so, the many engineers, material scientists, developed a way that one can create the materials really layer by layer control, such that now one can just confine the electrons or some of the entities in the extremely confined space in atomic scale. And those kind of space, which usually created by this MB techniques or other material growth techniques, allows us to create the materials with the kind of almost layer by layer engineered sessions. And the electron we can just kind of confine in certain areas in certain two-dimensional phase space. And this strong quantum confinement make this electron difficult to move out of the plane direction. Electron effectively move in the two dimension. So in this way, one can effectively create a two-dimensional phase space. And then one can study about this physics in the two dimension. Well, one may say that physics in the reduced dimension is less exciting compared with a higher dimension. But in fact, that was not the case. Once especially you drive the system in the quantum limits, such as go to the extremely low temperature, apply the high magnetic field, for example, that you can drive the system is extremely quantum mechanical. And especially in the inclusion of the many electron, system often just kind of provide so-called emergent phenomena, which actually cannot be explained in the simple term, and often requires a lot of the deep understanding of the many-body quantum physics. Good example is the fractional quantum Hall effect as a part of the quantum Hall family. Shankar-Dasama, after my talk, will probably discuss some part of this meaning of the topologies related with this quantum Hall physics, including fractional quantum Hall, right? So that's probably kind of the directions that we can think about how we can just move on to these low dimensions and interest in quantum physics. But yet another part of the two-dimensional systems that arises about 20 years ago. I'm starting with the first discovery of the graphene, a single atomic sheet of the graphite, which I also discussed yesterday in the Manda's talk and that Arindam's talk. That was kind of beginning of this series of so-called the layered van der Waals materials, atomically thin. Graphene is an example. Boron nitride, which is insulator. Transition metal dicharcogenide can be semiconductor, superconductor, and various kind, and so on. I think nature is kind enough to provide us a lot of different type of this two-dimensional materials, so-called two-dimensional material, atomically thin material, where effective description of the electron motion or the phonon motion is confined to two dimension. But also they comes with various different flavor. Some of them becomes metal, semiconductors, superconductors, and kind of various kind. And moreover, because this is a van der Waals interaction which does not care about the atomic scale of the bonding nature. So unlike the epitaxial system I just started with this talk, well-developed engineering technique, van der Waals, the materials also allows us to form the heterostructures, but without consideration of the epitaxial relation between them. And that provides us immediate kind of freedom to choose materials in different kind and combine them and with kind of different functionalities. Both Manda's talk and Arindam's talk yesterday kind of touch upon some part of this heterostructuring of this so-called van der Waals materials, right? Graphene alone, put in between the boron nitride, as Arindam actually mentioned, is a way that you can create the extremely high quality electron confined in the extremely confined two-dimensional space. And one can look at this the beautiful demonstration of hydrodynamic, but also once you apply the magnetic field and bring it to low temperature, like this electron in gallium arsenide type of the heterostructures, there's a quantum Hall and fractional quantum Hall effect sets in. Turns out in the graphene, especially once you move into bilayer graphene, you have not only so-called the odd denominator fractional quantum Hall, but often you can get also the even denominator quantum Hall effect much strong way, and will provide us a platform that we can study interesting many-body emergent phenomena. One thing that I want to mention briefly is it's not only the physics we can study, also this may provide us some way that we can just use this as a kind of interesting emergent technology, especially the quantum information processing. I will just briefly touch upon. For that, I have to kind of bring the one notions about the anyons. And it was already discussed yesterday talks. One can just create this, simulate the anyons in the superconducting circuits in kind of various core. But one can also create these anyons in the emergent system. I think this is kind of interesting part. Where quantum mechanics allows us to have any identical particle that classify the bosons and fermions depends on to their exchange statistics. Once you confine this the identical particle in the two dimension, already in the late 70s and early 80s, people just kind of discuss, there's a new possibility of the creating different type of the exchange statistics of the identical particle called the anyons. It comes around by just exchanges particle in the two dimension because winding number is a well-defined topological invariant in the cases. Often you can get these phases that with some fractions of this pi comes around. If the ground manifold is degenerated, often that the exchanges, the particle in the two dimension, often you may actually comes around after braiding, after exchange, you come up with a different mappings kind of possible by unitary matrix. And especially when you come with these non-abelian cases on that kind of degenerate manifold, by just kind of braiding of this anionic particle, that one may be able to encode this interesting quantum information is non-locally and can provide us some the vehicle to realize the protected quantum information processing. While this has been kind of interesting theoretical proposal, the real experimental materials that one can get realize anion, there has been some possibilities, and especially once you get into fractional quantum Hall, and where the ground state can be explained in terms of composite fermions, where the flux attachment on the electrons, they make this composite fermion particle, and can explain this the fractional quantum Hall states. It turns out any excitation of the typical, this so-called the Jane series of the composite fermion turns out the anyons with these abelian natures in there. And with the fractional charges and the fractional statistical exchange angle is what kind of govern this the anion quasi-particles in the this composite fermion cases. There's a particularly interesting the fractional quantum Hall also do exist, already discussed in the gallium arsenide fractional quantum Hall states in the 80s. The late 80s, it turns out that the so-called even denominator states that I briefly mentioned, something like the 5/2 in gallium arsenide, only can explain that in terms of the pairing of this composite fermion to make that kind of composite bosons, and condensation of this composite boson can explain this very weird, the even denominator states. It turns out the quasi-particle excitation of such a the even denominator fractional quantum Hall state is believed to be non-abelian. Therefore, just kind of using this one should be able to realize some interesting quantum information processing. And that's actually the heavy theoretical discussions already made, starting from kind of middle of the 2000s and so on. I think Shankar actually did the seminar also contributions in there. But basically, idea is if you have this non-abelian anyons, then distributed or created in the system by controlling their position and that exchange their location, you can encode this quantum information or the entangled informations distributed across the space, which can provide the protection against of this local perturbation, and hence come up with this the robust protected quantum information processing. So indeed, over probably past 10 or 15 years or so, that many experimentalists realized that the presence of the anion in the fractional quantum states, and particularly heading for this non-abelian anion, there has been progress, but has been rather slow process, and that's what I'm going to kind of discuss. One way you can detect the anion, including abelian and non-abelian anion, is looking at their interference signatures. This is kind of dated back to the idea of the Aron-Bohm effect, one of these, the incarnations of the Betty's phase in some sense, proposed by the Aron-Bohm in the late 50s. We know that charged particles undergo through the magnetic field. The phase of this interference of the two charged particles going into the two different paths is related with the magnetic flux that enclosed by this the path, and that can be detected in terms of the interference modulation, such as constructive or destructive interference, right? While that this is a kind of clear experimental proposal, realization of the observation of the Aron-Bohm effect take another 30 years, where experimentalists is develop the enough technologies to see that. And one of the examples is here. It is a gold ring made in the late 80s by electron beam lithography, small enough such that electron doesn't decoy or go through this the small ring. And then one starts to see that there's oscillation of this the current or the conductance that measure through this ring as a function of magnetic field. And those kind of period is precisely related with the magnetic flux quanta. That related with the charge E of the basic charge of the electron, right? Idea is basically using this type of the Aron-Bohm type of the techniques. What if that we just kind of create this the Aron-Bohm effect in the anions and just kind of look through those kind of conductance oscillation by the interference of the anions? Of course, as I mentioned, anion in the fractional quantum effect usually comes as a fractionalized charges, so we expect to see that maybe this period start kind of got changes, right? On the top of that, maybe if you just throw the one clever technique, one should be able to detect the kind of the interference exchanges pattern. I think that's kind of the idea. And of course, quite early on, starting from the 2000, where this idea comes around, people did try it out, did build up this interferometer based on the quantum Hall states, often called the quantum Hall interferometer. You know, the quantum Hall states, the current is carried by the edge states. So basically controlling the edge state, or that just design your device such that edge state is how that edge state kind of form. In principle, just kind of make the beam splitters out of the, using this quantum point contact, the partition between the edge states. One should be able to kind of create this, the electron version of the interferometer, such as Mach-Zehnder interferometer, Fabry-Perot type of the interferometer. One can design kind of various of kind. And already in the 80s, 2000s and 2010, here's the seminal work done by the Moti-Heiberlum's group, Mach-Zehnder interferometer. One starts to see that there's electron interference can generate this the nice patterns of the maximum and minimum patterns as changed by the magnetic field as well as the gate voltages, indicating there's electron interference one can detect. Similar things can be done with the so-called Fabry-Perot interference, and this one was done by Charlie Marcus some time ago. The Fabry-Perot interferometer with this the point contact can partition electron the quantum Hall edge states. One can see that those kind of oscillations in there. However, this observing the oscillation is easier, but looking at the Aron-Bohm effect was quite kind of difficult in here. Part of the reason is, unlike this metal ring that where the path is fixed, the quantum Hall states, especially when you change the magnetic field, you start to keep plugging this the flux quantas in there, and every flux quanta bring into new electrons there. So and those kind of new electrons that bring into the interferometer start kind of deform that your quantum Hall edge state area, right? So often that the areas also do change with the magnetic field, and that's kind of why the experimentalist struggles for the next 20 years to find out the device design and material design to realize this the unambiguous evidence of the Aron-Bohm effect as well as the exchange field. Turns out that 2020, about 5 years ago, it was a kind of really big year of this looking at the evidence of the anyons out of the quantum interferometer. And there are two groups efforts. So the first one comes from Michael Mumford's group at Purdue, and they designed the two-dimensional electron gas such that there's enough the screening from the ground plane is nearby, such that even if you just plug into the another flux quanta, it does not change the areas too much, and yet the ground plane is far enough such that it does not screen the other electron-electron interaction, so they get these quantum states, fractional quantum states. Here's a kind of example. So now they have the gate voltage which change the area, magnetic field, and again that checkerboard. I think this the red and blue shows maximum, minimums. The atom bomb effect goes on. Important part is those kind of slope is in these negative angles, which means that now they are seeing the really atom bomb signals. And more important part is they are seeing that those kind of jump of this phase. And turns out this jump is related with accidentally anion is jumping into their interferometer, and every time the anion is inside of the interferometer, the quantum edges which carry the anions around will start to make this kind of braiding operations out of it, and can provide you that the exchange angles, which actually appears as this phase break into this interference. So analyzing those kind of phase break, this group actually they definitely show that indeed that you can see that those anion braiding phase, especially this is 1/3 quantum state, there is 1/3 of fractional charges. You expect to see that 120 degrees of the braiding phase, they can detect kind of out of these experiments. About the similar time, that group led by the Gendar-Fab at Paris, they shows a yet different type of experiments. In this cases, they have this quantum point contact. Using point contact, they send this two anion across along this the quantum edge state, and that across the quantum point contact, anion start kind of scatters off. So in a sense, if you call the quantum point contact is a beam splitter, this is kind of close to the Hong-Mandel experiments in quantum optics done in the anions. So by just looking at the correlation of the scattering, they could kind of show that indeed those exchange phase of these anions in these beautiful experiments. So what you see here is the field start can progress about 5 years, and ever since that, I think that rather rapid progress has happening, and that's kind of something I want to kind of briefly share, especially related with the two-dimensional materials. Mentioned that I think that graphene has extremely high mobilities, and that the even denominator states appears in those kind of system readily. So having this interferometer graphene is another good platform one can realize, and you will see that having the graphene, making the graphene into the quantum interferometer, there's a lot of the advantage we also have coming from the versatility of this two-dimensional material. Making the system, making the quantum interferometer is kind of rather similar to what Adrian actually mentioned yesterday, except that now in these cases we encapsulate the graphene in between the boron nitride and graphite top and bottom, and we section the graphite to make this arrays of the top gates. Now you can see the barriers of this metal line is connecting this top gate, and put the top gate, basically we just can put the different density of the electron in a different location, which apply the magnetic field, set that what is a path of the electrons into the system. Especially electron path can be controlled to those kind of the structures that we created, such that we can create those the Fabry-Perot oscillators by just kind of designing of the top gate, right? And the result is once you just kind of apply the magnetic field and measure in the right condition and measure the conductance across this across the device, your conductance start oscillating, and this oscillation as a function of either magnetic field or the plunger gate, which changes the area of the interferometer, give us that the sense that we can detect the constructive and destructive interference of the system, right? Now, that what we expect to see that in the data is kind of following. So I told you that we can change the gate voltages, especially plunger gate voltage. And the role of the plunger gate voltage is changing the area of the interferometer. And then, of course, we can apply the magnetic field. And then electron will go back and forth in this cavity before it just escape it out. We can measure the conductance. So atom bomb phase that relevant for this oscillation interference is basically atom bomb, the flux phases inside of this the cavities, right? So you can see that that area and the magnetic field will give you that atom bomb phase, and then transmission coefficient across every pair of cavities that depends on those kind of phase, such that if you just kind of change both the field and the gate voltages, because those kind of two quantities multiply together, we'll see that the oscillation is changing this 1OB pattern. Experimentally, we are not measuring the all across a kind of large magnetic field and large gate voltages. Usually, we just kind of measure some small corners of this the phase diagram, and that's why this interference pattern is moving in this way. And if you remember, I mentioned that negative slope is atom bomb effect is basically related with this effect, right? So what we can just do the kind of following things. If I just measure the atom bomb effect, I should be able to measure the fundamental charge of the carriers that carry the currents around here. If it is electron, of course, that is the fundamental flux quanta. But if it is anion with the fractional charges, we should be able to see that those periodicity changes, right? Now, on top of that, now if you just kind of put the anions in there, now there is additional phase changes by the anions. That's kind of basically what you're going to see. I mentioned that once you create this interferometer out of the graphene or 2D materials, compared with the gallium arsenide, we have a lot of versatilities. For example, that the channel is rather exposed on the surface, so we can just put the additional gate is kind of rather easily. So unlike the gallium arsenide, where that it's limited, we can put the additional gate to control that QPC transmissions, kind of only QPC transmission without touching anything. And this gives us a lot of the freedom to tune around the experiments. And for example, that if I have this integer quantum Hall with the two edges kind of moving around, just changing the gate, the QPC gate, overhang gate, I can just partition the inside, inner state or outside state without changing any other condition, and you can start to see that those patterns looks kind of rather different. For example, that if I just kind of partition the inner edges, I got the regular atom bomb effect. But once I partition the outer edges, while the inner edge is just kind of isolated and look like the ring like the quantum dot, you can see the atom bomb effect, but there is always kind of some sort of phase jump and phase shift. And turns out this phase jump is related with the charging event onto this ring-like object inside of the sample, such that in some sense, this interferometer is also kind of sensitive to detect kind of charges, presence of the charges, and potentially the presence of the anion braiding phases in the right condition, right? Okay, so now once we get into this integer, now that that I just showed, the next step is now can I just do the fractions like the gallium arsenide? So our graphene device that I'm just showing here is extremely high quality, which means that with kind of decent magnetic field, we get this all kind of various different fractions. We first initially focus on the 1/3 of or the 4/3 of fraction, which is one of the strongest fractional quantum Hall states, where that excitation is supposed to be abelian anions, and whether we can just detect that information. So signature we are looking for is kind of two-part. One, because of the 1/3 or 4/3 is the abelian anions with the fractional charge of the 1/3 of the charges. We're supposed to see that the atom bomb phase is 3 times larger than what has been seen in the electrons, right? And the other part is once you just throw into this anions and as a localized anions, every time that a new anion comes in and that there's a braiding phase kind of appears, and that will give us about 120 degrees of the phase shift every time we just throw into this anion in the system, right? In some sense, that's kind of what the Manfras group did see in the gallium arsenide structures. So the first experiment that we did onto the high quality graphene device was rather disappointing when we just kind of moving into fractions. The first thing we noticed that is that device has quite of the instabilities in terms of signal. So I'm showing you here that just interference signal that we are getting out of our device with all the parameters are just fixed on just kind of time sequences, right? So if all the parameters are fixed, I should expect to see that just kind of stable signal, but that's not the case. You are seeing that signal is jumping around. And this is often that what we call the random telegraph noise and coming from some sort of the switchers into the device. And usually when these things kind of showing up, then we can say, yeah, your device is wrong and throw it out and we make the new device. But my students, Tom, who did this experiment, just noticed the interesting part. It's a random telegraph noise, but if you just look at it, at least there's 3 levels you can see, right? So the first question that he comes around and he charges on me is, well, why 3 levels? Why not 2, right? And then what he claims is, I think this 3 might be related with the fact that indeed anion comes in and give you the exchange phase of the 120 degrees every time anion jump in. So how many anion comes in? Basically, there is always a modulo 3 of this, the 2 pi. 2 pi over 3, right? So I think that's kind of can give you that this 3 the states. All right, so that is a plausible explanation, but there's no way that you can just use this noise data to prove indeed this one. But then he kind of suggests the following thing. We fix everything, just check the signal, right? What if we start to change any signal? So what if we just change the gate voltage? What if we change the magnetic field? The first thing that he did is change the gate voltages. And then every time you change the gate voltage, there are 3 different levels that shows up. So you can just plot it out, these 3 different levels, histograms, and that's kind of what he got. And once he showed this data, I was really blown off. I think that's basically immediately show that 3 branches of this the different anion numbers that appear the interference signal is just kind of presented without any computation. We can just count indeed there is a 120 degrees the phase angle apart from the device. I think this is kind of one of the rare moments. I think noisy data just kind of produce something quite exciting, right? In fact, actually, this type of the things is expected if there's a traps into the interferometer and the anion number is time dependent, then of course there's a phase that kind of shifts around during this kind of before that you make the completed this interference. You just shift on the branches, and there should be 3 branches coming from this the mode 3 type of the efforts onto the 1/3 of the anionic particle, right? So the one way, so in some sense we can see that now we can show that without any even calculation, your data immediately show that 120 degrees of the anion braiding phase. How about the fractionalized charges? Right. As I mentioned that you can just measure the around-the-bomb effect, and those kind of slope will give you the information about the charge. Right. If you just do this integer, that the slope will give you this with area of your device interferometer. You get this the charges that are making this oscillation for the integer. As I said, once you get into fraction, there's a switchers in our signal, so we cannot just do this type of the nice so-called pajama plot. If you just look at these switchers, this is the time sequences, right? I think every time you have the different random jumps around, so there's no way that we can create those kind of signal. However, I already showed that statistically we can just make this analysis, which means that instead of this taking individual trace like this, we simply kind of make the histograms out of this whole set of the data, and you get this at the fixed magnetic field, right? 3 different branches. Now we start to change the magnetic field and see how these 3 branches got evolved. Indeed, these 3 branches evolves really well with this the well-defined slope analogous to the slope, and the slope will give you 3 times bigger periodicities, which actually tells us that we have this fractional charges of the 1/3 of E. So in some sense, this experiment beautifully shows that indeed we can just measure both, although it's a kind of ugly noisy data, somehow analysis beautifully just give us that there are 120 degrees of braiding angles as well as these fractionalized charges. So we actually had this data about 6 months ago or something. I think we wrote the papers and put into the archive, and within few days we put the archive. I got the email from the Shankar, and then and when I get the email from the Shankar, I know that there's some mistake in the paper. And indeed, that's the case. And Shankar pointed out, and there's some problem into the analysis. And there's kind of 2 kind of the problems that he pointed out. I think I can share that. The first one is not only us, including Manfras, the original experiments onto this braiding. The point here is interferometer is different from the exchanges. Exchange is basically kind of changing the positions. It's 180-degree rotation if I just fix one on another one. But interference is basically going across every parallel interferometer is going 360 degree. So it is a different operation. So in a sense, it should be kind of the twice of these exchanges, right? So I thought kind of that is a kind of way of the kind of naming, instead of the exchange, I can call the braiding, but I think this paper kindly pointed out, even I cannot use a braiding because a mathematician defined the braiding as the same as exchange operation. So, all right, good. We changed the title, so it's a double exchanges or double braiding, doesn't matter. Okay, so that's the name. However, there's a more important and serious the point in this paper. It is because it's a twice of the or double braiding. There is ambiguity of the detecting exchange the angles. Because of those kind of 2I theta of the operation that embed into the exchange operation, always this the phase we can detect from the experiment is ambiguity of the sign changes. Right. In other words, if I just do this type of the experiment to the electron, I cannot just distinguish electron as a fermion versus boson. Right. That's kind of the part. Okay. This is a way that we can do that. Around the similar time that Steve Kiverson actually come up with an interesting idea about the kind of breaking out this the experimental issues with kind of following theoretical suggestion. It's a kind of following. If I have this Fabry Perot interferometer, 2-point quantum point contact, but let's assume that one of the point contact contains quantum dots of the containing anion, more precisely anion antidots in there, right? And then depends on this anion antidot is occupied and not occupied, there is kind of interesting differences in terms of interference. If it is empty, and then of course anion can just kind of go through this quantum point contact as before, then we get the same the interference phase as before. However, if the case that this anion antidot is occupied and there's kind of interesting cooperative tunneling process can be done, which means that first we just emptied out this the anion occupied anion dots, and then occupy this empty one with another anions coming from the another QPC. And outside of this, the tunneled out anions will just circulate around, comes back, original position. You will see that that's kind of exactly the same situation, except that we just kind of exchange these two anion position, 180 degree, right? So by comparing that the interference signal, in the presence of the occupied and unoccupied this anion quantum dot, one should be able to pick up those kind of sign changes. Now, while this the theoretical proposal is kind of really exciting, experimental realization, as you can imagine, is very difficult because you have to put yet another quantum dots at the QPC, which is very tough. It's not much of the area, and we barely control this QPC in the detail. But again, here the nature is kind enough, which means that when you just kind of sweep through the QPC, the transmission, often we can see that when QPC is energized and then kind of decreases, there's a sharp resonance we can see in terms of this the transmission across this QPC. And if you assume that this transmission is indeed related with some sort of resonance tunneling process of the sum of the localized state at the QPC, maybe this one actually we can just use anion quantum dot. One can actually show that as if that we are dealing with the quantum dot physics by changing this anion QPC gate voltages, also changing the bias voltages. Anyone work on the quantum dot, this is kind of what we call the stability diagram, right? This is bias voltage, this bias voltage is gate voltages. You can see every time you see that this peak, there's the diamond like the stability diagram shows up. If I just use the quantum dot analogies, I can see that at least this is occupied and unoccupied and occupied. And basically you can see that those the occupation number changes can be just kind of extracted out from this stability diagram. What we can do is basically controlling our gate voltage one position for another position and simply measure the interference pattern coming from these three different branches out of this random telegraph noise, assisted by the random telegraph noise. What you see here is that there are three branches, both shows up. Everything's exactly the same except a small change of QPC point. What you see here is that there's a 180 degrees of the phase shift or 60 degree of phase shift, half of 120 degree, which is kind of what is expected to see that those kind of phase angle changes across this formed and occupied and unoccupied kind of quantum dots. So you can see that we gaining that quite of this control now. I think in past probably 5 years or so, the community has been very excited about that kind of really fast progress happening in the both in gallium arsenide, both in graphene or other platform, start kind of manipulating these anions. At least we're starting from the the abelian anion in the beginning. So that give us kind of extremely kind of interesting the situation. So where we are going, the first thing that you want kind of demonstrate is can we just not only accidentally occupy this the interferometer with the anions, but can we actually controllably control the number of the anions in there? And that can be done by just putting this some sort of a gate structures on in the center. So this is completely doable technologically. So that's kind of one part move. The other part is, of course, so far we discuss only abelian anion. Graphene, unlike the gallium arsenide, non-abelian state is as strong as abelian states. So there's no reason that why we cannot just get this type of experiment done in the non-abelian anions, where that very strong even denominator states kind of comes around. Indeed, a few days ago, I saw that the papers posted by the Yuval Ronen's group, my former students working in the Weizmann Institute, beautifully show that indeed they just use the bilayer graphene. They start to see that this interference pattern with a E/2 oscillation period appearing in this the even denominator quantum oscillating bilayer. So showing that progress in this field is extremely kind of vivid. All right, so let me just kind of close my talk. That I want to kind of thank the all these students and the collaborator who worked on there. I think major work is done by the Tom and James. These two guys actually did most of the part that I just present. Christina is a new student joining. And Yuval Ronen, who actually initiated this project in my group as a former PhD student and worked in multi-high volumes group. Now he went back to the Weizmann University, and as I advertised, he started kind of produce his own very exciting result in competitions. So we have the collaboration with Ami Yakovi's group, and HBN coming from Japanese colleague in the NIMS, and a strong theory support by both Harper and Dima Feldman. Thank you very much for your attention.
Yeah, thank you very much for the very nice talk. We have time for questions. Please raise your hand and the microphone will come to you.
Okay. Philip, it's fantastic talk. Just very small experimental question.
Yeah.
So this is monolayer graphene.
Yes.
So when you create the Aharonov-Bohm ring, so how do you ensure that the central part of the ring is excluded from the electron transfer?
So
You etch it.
no, I think that it is a quantum state. So all the current state kind of flowing through the edge state, but edge is defined by this two gate voltages with a different filling. So
that's enough.
Yeah.
Okay.
Yeah, that's enough. Right.
Yeah, very nice question. Regarding this telegraphic noise, the trap charge, which is tunneling, they are in terms of electronic charge.
Yeah.
But the phase flux, you are saying that in terms of E/3.
Right.
So why does it happen?
Good
How do you
point.
understand?
Yeah. So therefore, that the charges that trapped kind of comes in is not the real electrons. It is anions. So what happens is when we just in the fractional quantum state, edgy state is occupied by these anions, right? That is kind of carried by the anions, right? That anion has it is kind of our reservoir, and that anion is kind of jumping into the somewhere in the trap site into our interferometer. I don't know whether I have that slide, but you can just do a lot of the different type of analysis. I just skip. For example, you can just do temperature dependent measurement, for example, and gate dependent measurement, and just kind of look through that. Where is the location of the this trap sites, and what is the energy scale, and what is the length scale? I think there's kind of various things, so you can just do that and convince that this is the anion traps rather than real electron trap. But if it is a real electron trap, as you said, that will not change the phase.
Yeah. So one very simple question is that what is this areas of this braiding regions, and what is your visibility of these oscillations?
Yes, so area that we are working on is about the micrometer square-ish. I think we try to make it smaller because you can see that visibility of the typical experiments, integer and fraction, That's around kind of somewhere in between 10% through the several tens of percent, sometimes even 50%. But this one is kind of strongly limited by basically what is a decoherence length scale. So although our experiment was done about the 20 millikelvin, still there kind of enough the decoherence kind of appearance by the electron-electron interaction. So the one way that we can reduce or enhance this visibility is making size small. So right now, the size of the device about the micrometer square. I believe that we can push that about kind of factor of 2 further. So kind of get increases a little bit more, but there's a kind of rather fundamental limitations to make it even smaller.
The worry is for the small gap states, because the moment you go to 5.5, the gap, the decoherence will increase significantly.
Yeah.
So it
Right.
needs to.
So that's kind of where I believe that graphene-based, the non-abelian anion interferometer has a little bit edges compared with gallium arsenide. Gallium arsenide, compared with this one of the well-developed gene sequences, if you go to the even denominator state, the gap is much smaller, about order of magnitude smaller. Graphene depends on to the magnetic field and displacement field, but you can get almost as similar gap as a non-abelian anion as abelian anion. So that's why size of the small gapness is not necessarily a problem that once you get into non-abelian anion in graphene. Yeah, Mandra.
Hi, Philip.
Yeah.
Very exciting talk. So the charging energies that you showed in the plot, there's a 10 power minus 6 B on top, which of micro electron volt. That sounds something.
You mean the later?
Yeah, the last slide.
Yes. Yeah. Right.
At the temperature, you're at 20 millikelvin, right?
Right.
So
right. I think this data at this point is a little bit grain of salt. You have to take it. I don't think that we can just take this as a kind of completely charging type.
Yeah. It would be kind of open dot.
Right. Yeah. So I think honestly that we got a little confused, because if it is electron quantum dot, I mean the charging energy and addition energy we can just think about. If this is anion quantum dot, first of all, that I don't think that I can just use any Pauli exclusion principles and how just kind of the quantum dot energy level look like. I think this requires a little bit of the thought. But if I just kind of look at those kind of is some sort of charging energy, it's not crazy number. But that whether I can just take that as a kind of really solid numbers coming from the quantum dot, that's kind of something we need kind of think about more. Yeah.
Last question. Sure.
So the approach you here, hi. It's
I don't see.
The same.
Yes. Same law.
yeah. So the approach you took is basically the interferometer approach. The other one is by this Febby experiment,
Yes.
Febby et al., where it's a time domain braiding.
That's right.
So what I'm curious about, see, the time domain braiding has to do with the fact that when you put a QPC, there are vacuum fluctuations. You create particle hole pairs, and then the injected quasi-particle can kind of exchange with the particle hole pair and create some signatures in transport.
That's right.
Now the question would be that when you are doing any QPC will do that. So don't you think in your experiment also somewhere the time domain braiding is anyway going on? So can one kind of bridge the two experiment and come up with some smarter thing which will have both inbuilt?
Yes, that's a very good point. Indeed, in fact, if you just look at the experimental proposals, even with the Fabry-Perot device, something like this, theory proposals how to realize that eventually you need kind of send the one anions across the braiding phase and then get the fermion parity. So there should be got to be the techniques. You should deal with the one anions through the QPC, like the Fabry experiments, right? So that's kind of eventually necessary condition. I would say that as an experimentalist, I have the great the respect of the Fabry group's the result, because that type of the experiments, sending the one charge, one wave pockets of the electrons or anions, that's not the easy techniques, and that integrating that into the system requires a bit of the efforts. We are just trying to do
saying that creating a leviton kind of excitation will be very non-trivial.
Yeah, that's non-trivial, and that's why that not many experimentalist group actually can do that, right? So I think that's kind of the way to go. I agree, and that's we are going to try to do as well.
Thank you.
All right. So let's thank the speaker again.
Thank you very much.